Section 9.6 is applications with rational equations. Okay, so we use rational equations every single day. So the three types of problems that we're going to discuss today are job sharing problems, distance, rate, and time, and shared costs. Okay, so here's the first example. So this is a job sharing problem. So it says Sydney can finish a 500-piece puzzle in about 8 hours. When Sydney and Megan work together, they can finish the puzzle in about 4.5 hours. About how long does it take for Megan to finish the puzzle if she works by herself? Okay, so these types of questions are asked all the time in like entry level, like freshman level math courses in college. I remember when I taught at IU, these were always on the midterm. And it would say things like, Becca takes 10 hours to finish a puzzle, and Cole takes 12 hours to finish a puzzle. How long does it take together? And I would have students every year that would be like 20 hours. Right?
No offense, but probably.
It doesn't make any sense, right? Why does it not make sense?
Because maybe Becca isn't doing any work.
Oh my God. Wow. Yeah, throw Becca under the bus. Maybe Becca's not doing any work. So it doesn't make any sense for that to take 20 hours because if they're working together, it should take less time, right, than it took Becca alone because she has someone helping her, right? So it should take less than 8 hours. Does this make sense? Okay, so there's something strange happening here, and what's happening is we have to think about the amount of time, or the amount of work that someone's doing per time period. So in each hour, how much work are they doing? Okay, so here's the best way to set these up. So if Sydney can finish a 500-piece puzzle in about 8 hours, then we say in 1 hour, Sydney does what fraction of the job? So if it takes her 8 hours in a single hour, what fraction of the job can she finish? 1/8 of the job, right? Does that make sense? She can finish 1/8 of the job. Okay, together, they do, this is kind of a weird way to write this fraction. It makes more sense if it was a nice whole number, like if it took 5 hours together, then they can finish 1/5 of the job, right? So if it's 4.5 hours, we're going to write it in a weird way. We're going to say 1 over 4.5 of the job. So how long does it take Megan to finish the puzzle if she works by herself? So we're going to let x equal the time for Megan alone. So in a single hour, what are we going to write for Megan? Not just x. What fraction of the job will she get done? 1 over x, right? So we're going to do the same thing. So it's like 1 over this, 1 over this, 1 over this. Okay, so it's going to be, so she finishes 1 over x of the job in 1 hour. Okay, so when we set this up, it's going to look like Sydney does 1/8 of the job. With Megan, Megan does 1 over x of the job. And together, they do 1 over 4.5 of the job. So it's Sydney plus Megan equals together. Okay, does that make sense how we set these up? All right, now there are other ways to do these problems with like charts and so on. If you know the chart way, that's fine. I know Sycamore is really big on the charts, so if you want to do a chart, you can. But this is probably the easiest way to set these up. Okay, so as we multiply through, we just talked about this in section 9.5, we can clear our fractions. We can multiply by 8, x, and 4.5, right? That can be our least common denominator. You could go smaller if you want to. It's easiest just to use all three denominators. So when we take this n, on the first one, our 8's are going to cancel, right? They go away. What are we left with? 1 and x and 4.5, right? So 4.5x. On the next ones, our x's are going to cancel, so that will go away and that will go away. Don't cancel them, though, on your paper. So we're left with 8 and 4.5. Oh, Becca's helping me. It's 36. And then the next one, the 4.5 and the 4.5's cancel, so we're left with 8x. Okay, so we have 4.5x plus, what'd you say, 36 equals 8x. We subtract the 4.5 over, so we get 3.5x equals 36. So when we take 36 divided by 3.5, Becca's my calculator today, what you got? 10.285? Okay. Oh, because this is how long it takes Megan. Okay. I was like, wait, it should be less than 8 hours now. Okay, this isn't the together. This is Megan by herself. 2 what? 286 if you round. Oh, okay. Did Karen get on your case about rounding incorrectly? Okay. 10.286, yes. Okay, does this make sense? Okay, so that's how long it takes Megan working alone. So if it takes Sydney 8 hours, it takes Megan 10.286 hours, then together we were saying it takes them 4.5 hours. Okay, it's taking them less time. Okay, so always kind of check that in the end to make sure you did it right. All right, so these are the guidelines for solving a job sharing problem. So you have your steps. So find the fraction of the job that can be completed by each person. So if you had 3 people, then it would be like Eric's portion in an hour, Riley's portion in an hour, Ryan's portion in an hour, right? Equals their portion all together, okay? So you can have more than just 2 people working together. Okay, so Michael and Alex share a paper route. It takes Michael 90 minutes to deliver all the papers. It takes Alex 60 minutes. How long does it take the 2 of them when they work together? So if we talk about our time period now, we're talking about minutes. So in a single minute, Michael could do what portion of the job?
No.
Close. 1/90th, right? Michael was the 90 minutes. So it takes Michael 1/90 to do. In a single minute, he can do 1/90th of the job. In a single minute, Alex can do 1/60 of the job. So the 2 of them working together, we're going to say 1/x. So x is the time working together. And then we solve it out. So you can make your common denominator something smaller, like you could do like 180. That would be easy, 180x. Or you can just do the 90 and the 60 and x. So I kind of just do all of them because I don't have to think about getting a common denominator on this one. So when I multiply this in, we end up getting 60x, right? Because the 90's cancel. And then on the next one, the 60's cancel. So plus 90x equals, and then the x's cancel, so 90 times 60. So we get 54 from the 9 times 6, and then 0, 0 on the end, right? So 5,400. So we get 150x equals 5,400. Karen, do you have your calculator out? Can you, what is it, 36 minutes perfectly? So it takes 36 minutes working together then. And think about it, does it make sense? Does it make sense that if it took 90 minutes for one person, 60 minutes for the other, that it's going to take less time working together? Yes, that makes sense. You're never going to go to IU or another college and say 150 minutes, are you? Say, no ma'am, I would never do that, never. Okay. I don't know how many of those finals I've graded. They were not my students, of course, other people's students. All right, so Ethan and Jack are painting a house. So working together, they can finish painting 2/3 of the time it takes Ethan working alone. Jack takes 6 hours working alone. How long does it take Ethan to finish painting a house alone? All right, so we're going to go ahead and set it up. So since I said it takes working together, they can finish painting 2/3 of the time it takes Ethan alone, I'm going to let x equal the time for Ethan alone, right? Because then together, I can relate it to x. So what do I want to write for their time working together? 2/3 x, right? So this one gets a little bit gross with our setup, right? Because we're going to have the 1/2/3 x, which is kind of gross. It's a complex fraction. We've talked about those. Okay, so as we set it up, we have Jack takes 6 hours working alone, so 1/6. Ethan takes 1/x, and together it's going to be 1/2/3 x. So you could simplify that 1/2/3 x, right? You could say 1 divided by 2x over 3 is 1 times, and you can flip it. So you could say 3/2x. So if you wanted to, you can make this 3/2x. It's the same thing. Okay, so if it bothers you that it has that complex fraction, then just simplify it. It's fine. Or you can just go with it. If you just go with it and you do the same kind of pattern we've been doing, you multiply by 6, you multiply by x, you multiply by 2/3. I'm not going to do another x, though. Do you guys see why I don't need to do another x? Based on our common denominators last time. You could do another x, but it just kind of makes it bigger than you need. So when we multiply it in, our 6x and 2/3 are going to reduce out with that 1/6, so the 6's cancel and I get 2/3 x. Plus the x's cancel and I get 6 times 2/3. And then my x and my 2/3 cancel and I'm left with 6. So I get 2/3 x plus, what's 6 times 2/3? 4. Yeah, so 4 equals 6. I subtract the 4 over, so I get 2. Okay, and then I'm to the point where I have 2/3 x equals 2. So if I want to clear that 2/3, I can do it all together. So Logan, what do I multiply by to get rid of that 2/3? Yeah. How are you, Logan? Logan really wanted to tell me. So multiply by 3 over 2. So I get x equals 2 times 3 over 2, so 6 over 2, which is 3. So the time it took for Ethan was 3 hours. So how long would it have taken them working together then? What do you guys think? 2/3 of 3. What is 2/3 of 3? 2. Yeah. So it would take them 2 hours together. All right, so some teachers make you kind of write that final sentence. If you want to write a final sentence, that's fine. As long as you've defined what your x is and I know what you're solving for, I'm okay if you don't. So the final sentence would be, it takes Ethan 3 hours working alone. All right, so Morgan and Jamie use hoses to fill up Morgan's swimming pool. Have you guys ever filled up a swimming pool with a hose? It takes forever. So they're deciding to use the neighbor's hose as well. So both hoses take 18 hours to fill the pool. So Morgan's hose used alone takes 20% less time than Jamie's hose used alone. How much time is required to fill the pool by each hose alone? So since it says 20% less time than Jamie's hose, I would let x equal the amount of time for Jamie's. And then 20% less time. Okay, who thinks they can answer that question? 20% less time. 4/5. You could do 4/5 x. Typically when I do like 20% less, I'll write 0.8. But that's right, 4/5 is 0.8, right? That's perfect. So 0.80x or 0.8x. Does that make sense? You take 20% off of 100%. So you have 80% left. So that's going to be Morgan's hose. So putting it together, we have 1 over x plus 1 over 0.8x or 0.80x if you want equals, together it takes 18 hours, so 1 over 18. So in a single hour, both of them did 1/18 of the job. Okay, makes sense? I'm going to clear it all out. So multiply by x, multiply by 0.8. You can do x again, but I probably wouldn't since you already have the x and then 18. So the x's cancel, so we get 0.8 times 18 plus 0.8 and x cancel, so I have 18 equals 0.8x. So 0.8 times 18, what is that? 14.4. This table over here is helping me with my calculating. The rest of you guys don't even have your calculators out. Okay, it does. It's not on now.
I do.
All right, good. So 32.4 equals 0.8. All right, so what do we get, Chris? You told me you have your calculator out. So 32.4 divided by 0.8.
You get 40.5.
40.5. So it takes 40.5 hours then.
It's okay.
It is. You should try to fill a swimming pool with a single hose. That's why you see those trucks with the big hoses, right? Have you seen those? Yeah.
I have a pool in my backyard and we have a fire hydrant.
Oh. How do you do that? Like you call like the fire department or something?
Like a pool company has a really big hose.
Oh, okay. Yeah, I've seen like those big pool trucks that have like water in them. Have you guys seen those with the big hose? Yeah. All right, so it says charts often help with distance equals rate times time problems. So you don't really need the chart for these working together ones necessarily. They do get kind of complicated. There can be harder examples that we can talk about. But these ones, the distance equals rate times time, I would probably do a chart. It's really just the best way to organize the data. So it says Alex flew his plane for 580 miles directly into a strong wind and then flew back in the same wind. His total flying time was 5 hours. If the plane speed without any wind is 240 miles per hour, what is the speed of the wind? So have you guys ever traveled to like Europe, let's say, and on the way there, it takes you maybe 8 hours to get there. And then on the way back, it takes like 10 hours. Have you guys ever experienced this?
Jet stream.
Yeah, so what's happening? The jet stream, right? So you got some kind of like, as you're going there, the wind's pushing the plane faster, right? So maybe the pilot is going, this is pretty slow, 240 miles per hour. This is a small plane. But maybe on the way there, that's going like 500 miles an hour. I don't know how fast they go. But then the wind's pushing it even faster, right? So maybe it's really going 560 miles per hour or 600 miles an hour, right? So Becca's saying the same thing happens with cars. Have you guys noticed that when you're like going with the wind with a car and you can kind of feel it? Usually you feel it like side to side. When you're like passing a truck, all of a sudden you're like, whoa. Has that happened to you guys before? Yeah. Oh, interesting. Yeah. So she's saying she drives to Wisconsin and the gas mileage is worse on the way home because of the wind. Interesting. Okay, so we're going to set this up. We're going to do a little chart, and we're going to do distance equals rate times time. So I usually do rate, time, and distance. And I know that rate times time is equal to distance. We talked about that formula just the other day. So let's say with the wind and against the wind. Okay, and the question at the end says, what is the speed of the wind? A lot of times in story problems, I would say like 90% of the time, the very last thing they ask for is usually what you should let your variable be. So what is the speed of the wind? We're saying let W equal speed of wind. Or X if you prefer X. Okay. So the total distance for both of these is 580 miles. He goes 580 miles there, 580 miles back. And his total flying time was 5 hours. But he didn't go 2.5 there and 2.5 back necessarily, right? So we can't put anything there yet. Now our rate, though, was 240 miles. But if he's going with the wind, does he go faster or slower? Faster. So we're going to do plus W. Sorry. So he went faster because the wind is pushing on him. And then against the wind, we had 240 miles per hour, and then minus W, exactly. So if you set this up with a chart, there will always be one section of the chart that isn't filled in. Okay, and that's our time. We don't know how long it took him. We don't know if it took 2.5 hours there, 2.5 hours back. Probably not, right? Because he's going faster on the way there. So we're going to use these other two columns to figure it out. So if I'm trying to solve for t, and I have rate times time equals distance, do you guys see how the time is equal to the distance divided by the rate? This is where our rational equations come into play. This is why we learned section 9.5 before this one. Because we're going to take this distance, 580, and we're going to divide by the 240 plus W. So we're going to put in here 580 divided by 240 plus W. And then this other one is going to be 580 divided by 240 minus W. And what should they add up to be? 5. That's going to be our equation. So as long as you're setting it up the same way, you'll be fine. You got it. So we're going to say 580 over 240 plus W plus 580 over 240 minus W equals 5. Done. And then we solve it out. So we're going to multiply everything through by the denominators, 240 plus W, 240 minus W. So on the first one, the 240 plus W's cancel, so I have 580 times 240 minus W. And on the second one, I have the 240 minus W's cancel, so I get 580 times 240 plus W. and equals 5, and then here's the lovely 240 plus W times 240 minus W, like that. So you definitely want a calculator out. I'll give you a second to try this. So you're going to FOIL here, and then multiply that 5 in, and you're going to distribute on the other side and simplify. So go ahead and try it. All right, so you should multiply the 580n, and you should get 139,200 minus 580w plus 139,200 plus 580w. So the 580w and the negative 580w cancel. Did you guys get that? And equals 5 times. And when you FOIL this out, your outer and inner terms will cancel, right? Because of the difference of two squares. So you get 57,600 minus w squared. So when you distribute the 5, you get 288,000 minus 5w squared. Okay, do you guys have that? So now we're going to subtract the 288,000 over. So we get 278,400 minus 28,008, or 288,000, and I get negative 9,600 equals negative 5w squared. Yeah. Yep, you could if you don't want negatives, you could do that. Now if I divide by negative 5, I get w squared equals 1,920. And so my last step, square root, right? So I'm going to do the square root of that answer. So I get w equals plus or minus 43.818. Does the negative matter? Our wind is not going to go in negative miles per hour, right? So, I mean, kind of, if you consider direction, but we're not going to consider direction. We'll just make it, the wind is 43.818 miles per hour. Okay, and that's our answer. Tricky, huh? Okay, so we'll do one more. So they're not going to be that bad. I won't put one like that on your test most likely because it takes a lot of time and I don't want you to freak out in the middle of your test. If you want another one like that for practice, you have number 3, which I have kind of set up in the chart for you. But let's do one that's more like what I would probably put on the test. So it says Mrs. Thompson's boat goes 20 miles against a 5-mile-per-hour current and then heads back again. Her trip took a total of 3 hours. What is the boat's speed in still water? Do you guys know Mrs. Thompson loves her boat? She loves going out on her boat all the time. So we're going to set it up. So we're going to have our distance equals rate times time. So rate, time, distance. You can box it in and make the big chart if you want. Okay, and we're talking about with the current and against the current. Okay, and current is very similar to wind. So you guys have experienced this before. Have you guys ever gone like canoeing? And if you're going against the current, it takes a lot of force, right? You're really trying to canoe. You're really paddling. Becca knows this is true. Becca, do you know the first time that I went canoeing? I was like 8 years old, and I went with my older sister and my twin brother. And I was in the back of the boat, and I was trying so hard. I was really weak. I'm still weak, but I was like really trying to canoe. But I was doing it this way because, I mean, it makes sense to an 8-year-old. I wanted to go forward, so how do I take my canoe? I pushed it forwards because I wanted to go forward. And then my sister finally realized like 3 miles into the trip that I was doing that. Whoops. So she was pretty mad at me. But yeah. Oh, I wasn't making it turn. I was just resisting against her, right? Okay, so anyway, so if we go 20 miles against a 5-mile-per-hour current, so that's how fast the current is. We want to know the boat's speed in still water. So if there had been no current at all, how fast could that boat go? So x is boat speed. So with the current, the boat is going to go faster. So it's going to be x plus 5, right? 5-mile-per-hour current. And against the current, it's going to go slower, x minus 5. The time, we don't know still. But we know that she goes a total of 20 miles and then turns around and goes back 20 miles. So that's where we're filling in this time again. So do you guys get it? Do you see what it's going to be there? So it's going to be the 20 over x plus 5, and it's going to be 20 over x minus 5. And that's going to give a total of 3 hours. So these are a lot more manageable numbers, right? Would you guys be able to handle this if I put something like this on the test? Luke still gave me the side eye, like, please don't put this on the test. You get 100 anyway, don't worry. I should just cancel it and not give a test.
Yeah.
That'd be nice of me. Yeah, this test is not going on the updates, so sorry. All right, so it's going to go in like that. So we're going to have x plus 5, x plus 5's cancel. So we get 20 times x minus 5. Plus x minus 5, x minus 5's cancel. So we get 20 times x plus 5 equals 3 times x plus 5 times x minus 5. And we just solve it all out. So we get 20x minus 100 plus 20x plus 100 equals 3, and then the outer and inner terms cancel, so when we FOIL it out, we get first and last. So x squared minus 25. Cancel, cancel, 40x. You can just kind of write the answer if you want to just pay attention and write the answer, that's fine. So 3x squared. Oh man, I forgot that this one is not going to be very nice. Because this one's different than the last one, isn't it? So what's different about it? Yeah, you actually have to like factor it out, right? So we're going to get the 40x over. So we're going to have 3x squared minus 40x minus 75. Let me go down here. Okay, and we can factor or we can use quadratic formula. I don't know, does anybody have it factoring? Did you guys get it? 3x plus 5 and x minus 15. Oh man, you saved us. So we end up getting x equals negative 5 over 3 and x equals 15. So which one do we think is the boat's speed? 15 miles per hour, right? That's it. Okay, does that make sense? All right, so let's stop there. Scroll down.